get started here. Let me begin with a word of prayer. So, Dearly Father, we thank you for this day and for this time and this wonderful large classroom we have to use since everyone else is assessing. Help us to just learn a little bit more about math today and to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so we were to adjoints, right? I defined what the adjoint of a linear operator was, right? And I proved that the norm of the adjoint of an operator is equal to the, right. So, continuing that discussion, basically. So we had a mapping from a Hilbert space to a Hilbert space, a linear transformation, right? A star is also a mapping from H to H, defined as follows. Basically, you just have AX with Y is equal to X A adjoint Y. All right? And you can prove that if you have such a if you define the operator by that, it is in fact the linear operator and so forth. So this is all right, and we proved last time that the norm of the adjoint is equal to the norm of the operator. I think that's assuming, of course, that the operator is bounded, right? Because there's no reason for the norm of A to be calculable in general, right? And also, we had that the norm of, I want to say, A star A is equal to the norm of A squared, again, in the context of the norm of A being a bounded operator. Let's see here. Although I guess I didn't prove that, but it is true. So he has an example which I think is kind of nice and easy. He has his example. He's like A of Z1, Z2 equals to Z1. So it's easy enough to see that this is a linear. Wait a minute. Oh, my bad. I was about to say this is not going from H to H, but that's because I have copied it down wrong. It is 0, Z1. Okay, so there you go. That's what he gave. All right, so then this defines A, right? And so let's see here if we can calculate the formula for A, the adjoint. So so here this is a, for all Z in C2, right? So if we take the inner product of, let's say, AZ with W, that is supposed to be equal to Z with the AW, right? So what you're looking at is the inner product of 0, Z1, comma, W1, W2.
Is this when A is self-adjoint?
No, I just...
Oh, okay.
Yeah, thank you. No, that's just a typo. It's nothing so profound. And so we don't know what this is yet, right? Okay. All right. And okay, how does this work out? Well, this works out to, you remember what the formula is for like the inner product of Z and W and C2? It's how's it go? Z. Let's see. This is what a 2 by 1. Z is a 2 by 1 matrix, right? So I want Z transpose W conjugate. That's the formula for it. That's what I was forgetting. So that's the formula for the inner product on C2. Well, so that's the inner product formula for the inner product on Cn. And But anyway, so, all right, so we've got, 0, let me just write over here. So I have the row vector 0, z1 times w1, w2 is equal to, the row vector conjugate, right? z1, z2 times the, well, what I don't know, right? Let me call it A star W1, A star W2, right? And so that gives me what? That gives me Z1 W2 bar is equal to Z1 times the conjugate of, not the conjugate, adjoint of acting on W, the first component, conjugate, plus Z2. I'm quite certain this is not what's in the book. I'm not looking at the book. The book has something more clever, I'm sure. Conjugate, right? All right, so we're trying to figure out the formula for the joint from all this. If I put Z1 equal to 0, what happens? Yeah, I get Z2 times A star W2 conjugate equals to 0, right? But since this is holding for all Z2, this implies that the conjugate A star W, the second component of it, is equal to 0.
Because, or Z's are in Z2, which is the old.
Right.
So, what's going on?
Yeah.
Okay.
Because of course I could put like, Z2 equal to 1,
Oh, yeah, gotcha.
and that holds for arbitrary. All right.
Yeah. Oh, for all, yeah, gotcha.
Now on the other, so now I know that that's 0, right? And then coming back to here, right? I can put Z1 equal to 1, and I get A star W conjugate, the first component, right? Conjugate is equal to what? It's equal to W2 conjugate, right? Which then tells me that A star W is actually just equal to W2 comma 0, putting it all together. See, because I know that the second component's 0 from this, and this, when I take the conjugate of both sides, gives me that the first component of A star W is W2. So, now, this is a really dumb way to do this, because a much simpler way would be to use the theorem we'll find soon enough, which is that if we look at A as a matrix, right? The matrix of A, you're fine. The matrix of the adjoint, we actually can prove it's the matrix conjugate transpose, right? Today, I might even prove that last time. I forget. So, what's the matrix for A? So you're going.
Yeah, so 0, Z1 bar. Oh, sorry.
So, all right, so if we put in 1, we get, so like putting in 1, 0 gives me 0, 1, right? So that tells me the first column of the standard matrix is 0, 1. If I put in 0, 2, that gives me the 0, 2, 0, 0. So this is A. So the matrix of the adjoint is then 0, 1, 0, 0. Okay, so that's not, which is this formula. So, okay. All right, now I've given entirely too much detail about this really simple example, so let's go on. Definition. Actually, if I don't mind, I'm going to erase all this because this will not be really of interest going forward in this lecture. So what does it mean for it to be self-adjoint? Self-adjoint means that it is equal to its adjoint, right? Of course, I know that you know that already because of your question earlier. But so definition A, self-adjoint, A is equal to A adjoint. All right. And that implies, so if if the matrix of A is equal to M, then this implies, if it's self-adjoint, it implies that M conjugate transpose is equal to M again, right? When we sort through it. And then typically in physics, it's the Hermitian conjugate equal to M again. So this is called the Hermitian matrix. So the matrix of a self-adjoint operator is a Hermitian matrix. Now, of course, I'm talking about the context of a finite dimensional complex inner product space. Although example 4.45 says if you're working with a separable infinite dimensional Hilbert space, then you can also talk about the Hermitian conjugate for an infinite matrix. So this equally well applies in the context of a infinite dimensional but separable Hilbert space, where we still can talk about the infinite matrix reasonably with respect to that orthonormal sequence. Definition, next example here. So I guess this is example 2. Oof. Well, this marker's no good. Example 2. I keep skipping over this example. It's appeared in previous sections, but I haven't, give it any airtime yet. But this is the so-called Fredholm operator. And it on L2 AB, so the twice Lebesgue integrable functions here, in closed interval. And so the definition of this thing is Tx of S is equal to the integral from A to B of K of St times x of t dt, where we're assuming that the double integral over the rectangle AB cross AB of the function kst absolute value squared ds dt is finite. So he says, note that this condition is satisfied if k is continuous, all right? And then he's going to give us a proof that, in fact, this Fredholm operator is self-adjoint if we have a particular condition. So let's see if we can discover that condition, right? What condition do we need on this function k to make the Fredholm operator T self-adjoint, all right? And so to calculate that, we need to look at the inner product of Tx with y. Now, this is the inner product in L2, right? So that was defined to be the integral from A to B, I believe, of Tx of, well, let's say S times y conjugate of S ds, I suppose. if I'm using that variable there. And so then, of course, he then plugs in the definition of the Fredholm operator, and this becomes a double integral in this sense. It's an iterated integral, right? So k of st x of t y of s conjugate. And you can, I suppose, I mean, I guess dt comes first. Well, he's got the s first, but I guess the condition that that integral's finite allows you to do the integration in either order and get the same amount, same event.
Are we using Fubini's?
Yeah, I think we're using Fubini's theorem to flip the order of the integrations there. But anyway, then what he does, then what he does here is what's he do? He takes the conjugate overall. So he takes the conjugate of the whole thing. All right, like, so I'm going to write it in the step above. All right, like he does this.
Yeah.
But then he takes this lower conjugation and applies it to the integral. And so what that does is it applies a conjugation to this piece here, and it double conjugate to that, which erases that. And then you have, you know, integral from a to b, integral from a to b of y of s t of oh, wait a minute. I want to, well, hold on a second. Hold on a second here. I want to, fine. Well, nope. Nope. Sorry, I'm thinking. I mean, we're trying to get x t of y, right?
Yeah. Are you showing t is self-adjoint?
Yeah, so,
Okay. Yeah.
so I want x t y here. So I guess I need to leave the x. I need to leave this x here conjugated.
Oh, we probably are
And
we got k bar.
yeah, k of s t bar. I mean, I'm not doing anything yet. Y of s dt ds. And still the whole thing is conjugated, right?
Yeah.
So then he's like, well, that's the integral from a to, let me stop writing in red here. Then that's the integral. Integral from a to b. And then he uses the conjugate to rewrite that as x of t. Then he's like integral from a to b of k of s t y of s. Guessing that ds goes here, dt. But he's got a conjugate over all of that. So this is still there, and the conjugate still goes over all of that. Okay, that makes sense. That's just directly. Yeah. So,
So T is T,
so this is,
TXY.
so what's under the bar, right? What's under the bar is, what's under the bar, we could say is the T star acting on Y. Of S. No, of T. Right? Because this, I mean, this, we're blah, 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 blah. Integral from, so you know, we've got integral from A to B, x of t, t star y of t conjugate dt. That is working backwards from what I'm expecting, right? X t star of y. I mean, so this is t star of y is the definition of the adjoint. This is the definition of the inner product on L2. And I'm just making the identification that the thing under the conjugation has to be the adjoint here. So altogether, we have that t star y of t equals to the integral from a to b of k of st conjugate times y of s ds, right? My bad. Well, all right, so now he rewrites this as the integral from, so he says that t star y of s, all right, is equal to the integral from a to b of k of ts conjugate y of t dt. So he then changes letters on us, which is fine. I mean, they're variables. You can flip the s and the t, and he does that so that you can more readily see, in order for this to be equal to t star y of s, what do you need? I mean, in order for this to be equal to t, in order for that equal to the ty of s, what condition? Oh no, you're fine. Sit down. What? It was actually within frame anyway, mostly. What do you need there? Well, you look at the. Yeah, we need for this right here to be equal to what?
It's the same thing, its own conjugate.
You need-
Oh, it needs to be symmetric.
Right, so yeah.
Yeah.
So if k of ts conjugate is equal to k of st, then the Fredholm operator, you know, T is self-adjoint. Which is what he says. So that's kind of it's again, it feels pretty much like the matrix thing, right? It's kind of like a transpose. It's like a conjugate transpose, isn't it? Yeah. You flip the inputs, and I mean, but this is, so in some regard, I guess intuitively speaking, if you can kind of think of this as like an infinite matrix with a pair of continuous indices. Think of S and T as continuous indices. I mean, this is in some sense also a Hermitian condition
Yeah.
at the level of infinite indices, continuously infinite indices. Okay, anyway, so his next example, which I will try to go quickly through, is this. He has ax of t equals to t times x of t. So just multiplication by the t. And you can check that this is a linear operator on L2AB. And it's pretty easy to check that this is self-adjoint if we calculate it. Inner product of ax with y, integral from a to b, tx of t, y conjugate of t dt, which he points out is, this is very silly, the integral from a to b of x of t times t y of t conjugate dt. So you're like, well, it was t. Well, t is a real variable, so it's equal to its own conjugate. See, x and y don't have to be real valued. But, you know, we're talking about a complex valued function of a real variable. And anyway, that's x a of y. So that shows you that a is equal to a star. All right, so that one. And then he has another example, which I'll skip. Let's see here. What else does he have to tell us? If you have phi, a bounded linear functional on H, let's go ahead and I'm going to write these theorems over on this board over here. I think we're done with this example for now, yeah? Okay. This Fredholm thing does come back up in interesting differential equations. And like, it has something to do maybe with like the theory of transforms also. Things like, well, maybe that's not exactly true, so let me not conjecture too much, but I have seen that when I wasn't looking for it in other things I've studied. With like, I had a mini course I did with students on partial differential equations a few years ago. And I remember something like that in our study of Green's functions. All right, so let's see here. Let phi be a bounded bilinear functional. What does that mean? Bounded bilinear? What was a bilinear functional?
Well, part of sesquilinear.
Oh, right. So phi is a mapping from H cross H to C, right? And it's bounded, so yeah. So bounded bilinear functional, and let A be an operator. Such that phi of xy can be equal, it can be written as the inner product of x with ay. All right? Then A is self-adjoint if and only if phi is symmetric. So let's see here. So if we have x ay equals to ax y. Oh, okay, I'm sorry. I'm jumping steps here. Let's do this right. So, all right. I'll start with phi yx, right? I'll conjugate that thing. So that would be the inner product of y with ax, right? But that's equal to ax y, right? by the, that's the inner product, right? And then this is equal to x a y by the definition of the adjoint. And if it's self-adjoint, that's this, right? And so that's essentially the calculation which supports it. Like, if, and of course this is what? Yeah.
So it's just that they only have this just full straight.
Right. So like if phi is symmetric, then well then this is equal to that. Consequently, these are equal. And then if A is self-adjoint, then this is equal to that. So it's essentially this calculation that proves this theorem. And then, all right, let A be a bounded operator on a Hilbert space. All right, I'm gonna go over here. Actually, I'll do it up here. So theorem A, H bounded. Oh yeah, thanks. Then T equals to A adjoint, and T2 equal to A plus A adjoint are self-adjoint. So, I mean, the proofs of these things are fun. So if you do like x with, oh my bad. If we do, let's say, you know, a star x, right, with y, then that is a star x with a star y by definition of the adjoint. So, you know, this is the composition of A with A star x, right? And then this is equal to, let's see here. Oh man, did we already prove that the adjoint of the adjoint? Do we have that the adjoint of the adjoint is the, oh yes. That was the direct consequence of the property definition. So back on page 158, we mentioned that the adjoint of the adjoint is A again. So he says that follows directly from the definition of adjoint. So here we have adjoint, A, adjoint, Y. But this is just x with a adjoint, y. But of course, by definition of adjoint, this is x a adjoint, y. You know, because going directly from here to here, we have that. But since this holds for all x and y, and since these are equal for all x and y, it implies that a adjoint is of course equal to a adjoint, which is to say it's self-adjoint. All right. And the proof of the other one, if we look at, you know, T2 x comma y, then that is equal to A plus A adjoint x comma y, which is, this one's even easier, x A adjoint plus A, well, my bad. This is x A plus A adjoint y, But then by properties of the adjoint of the sum is sum of the joints. So that's A adjoint plus A adjoint adjoint, which is just A again. You'll forgive me if I don't write that down. But then these commute, so this is equal to so therefore T2 is equal to its own adjoint. So T2 is self-adjoint. All right, what else can I? So I'm going to erase the purple now. I won't erase the blue yet. Next theorem is that the product of two self-adjoint operators is self-adjoint if and only if the operators commute. Theorem T1 and T2 self-adjoint, then T1 T2 star equals to T1 T2 if and only if T1 T2 is equal to T2 T1. And of course this is a statement about composition. This is again pretty easy to prove. It's pretty much direct calculation. So if we look at T1, T2 acting on X with Y, again, all of this is for linear operators on a Hilbert space, then that is T2 of X, T1 star of Y, right? Oh, cool.
Sorry about that.
No, it's fine. And then, well, this is X T2 star T1 star of Y. However, we're assuming that T1 and T2 are self-adjoint, right? So this is literally T2 T1 Y. And the theorem follows, because this is, you know, if this is true, then this is equal to that, which shows you that this is equal to its adjoint, and vice versa. So it's just... if you have a self-adjoint operator, then any polynomial of that operator is also self-adjoint. So if I have, if A star is equal to A, then a polynomial in A is also self-adjoint. Where here P of A is understood to be like alpha 0 plus alpha 1A plus alpha 2A squared plus dot, dot, dot. And so here's one of the really kind of sad things about too many math majors not taking differential equations is like, you guys don't, man, you don't really get a lot of exposure to polynomials of operators. Oh, see, this is why I need to teach different, oh man, if I'm teaching linear algebra, I can fix this. I'll just insert about a week of differential equations into linear algebra, then we'll all be okay.
Operator system, linear.
System in linear a little bit?
Yeah.
Yeah.
But not in general.
Well, but that's good. So you've seen some, but this is a, you know, to form a polynomial of an operator, it makes sense. It's just the product becomes composition, and these are just scalars. But anyway, okay. So all right, next theorem. Next theorem is that if you have, for every bounded operator T on a Hilbert space, there exist unique self-adjoint operators A and B. So if T is bounded operator on H, then there exist unique self-adjoint A and B operators for which T is equal to 1/2. Oh, my bad. Oh, sorry. My eyes keep jumping to the wrong line. So T is equal to A plus IB. And T adjoint is equal to A minus IB. Of course, you don't really need to say both of these things. If you have this and you have that A and B are self-adjoint, then this automatically follows by the properties of the adjoint given at the start of this section. So this starts to give you a better sense. I mean, like, what does it mean to be self-adjoint? In some sense, they're kind of like real, right? This is like the real imaginary breakdown of an operator. So you can think about things that are self-adjoint as sort of being real valued, or well, real operators. I don't think I need this bounded bilinear functional mumbo jumbo here anymore. Let me get rid of that. All right, so the proof is probably instructive because it's reminiscent of other things. So A, 1/2 T plus T adjoint. B is equal to 1/2I T minus T adjoint. And then it's automatic. First of all, it's manifestly clear that this is equal to its adjoint. I mean, the first one is just obviously equal to its adjoint, because if you take the adjoint, you get that goes back to itself, and this is T adjoint, and then they commute, so it's the same thing again. This becomes T adjoint, this one becomes T under the adjoint, but when you hit the adjoint, when you adjoint a scalar multiple, it conjugates it. So this gives you minus 2I, and so then they flip, and you get B adjoint. So it's again a straightforward consequence of the properties of the adjoint at the start of the section. And he proves. Oh well, he does prove actually. He doesn't, he doesn't use properties of adjoints to prove that this. When you take the adjoint of this, you get the other one. He just does a calculation on the inner product to prove that the adjoint of T is equal to that. So you can look at that calculation if you want on page 162. How do you what's the norm of a self-adjoint operator on a Hilbert space? The norm of a self-adjoint operator T on a Hilbert space is the supremum of the over the unit ball, I guess. X norm X equal to 1 of the absolute value of the inner product of Tx with X. And proof of that's actually about a page. So this is not an entirely trivial comment here. This theorem. What's the definition of T? The norm of T, rather. It's it's almost this, right?
Yeah, except without it.
Well, actually, kind of. It's not. Well, yeah, but I mean, yeah. Okay, great. Yeah, you're right. So I don't disagree. But what's the difference? I mean, correct. This would be what? It's just square root. Yeah. So it's it's awful close to that. So it's almost like there's just a missing t here.
Yeah. Huh.
You know, although it is modulus, not square root, isn't it?
Yes, because interpot can be complex.
Yeah. Oh, but of course you don't need the modulus here because you know, remember that the inner product of a vector with itself is positive. It's real. So, but anyway, it's an interesting theorem. So the one direction of it's pretty easy. The one direction of the theorem, basically, you just start with the Cauchy-Schwarz, you know. So you start with the absolute value of tx with x, right? Is less than or equal to the norm of tx times the norm of x, right? But that's equal to the norm of tx, since we're working on the unit in the context of the unit vectors. And then, remember, we have proved that this is less than or equal to the norm of t times the norm of x, since t bounded, right? Any bounded operator on a Hilbert space is the product that the norm of the operator is less than or equal to the product of the, you know, the image is the norm of the operator, the norm of the input. This is a theorem we had for bounded operators. And then, of course, again, we're looking with unit vectors, so that's equal to norm of t, right? So this shows you that the this quantity, whatever it is, right, is less than or equal to the norm of t. So it's.
Did we say norm of t is arbitrary upper bound, so the supremum of
So that gives you one direction, and then on the other direction, he does things that are much more mischievous. On the other direction of things, no, you're fine. I need to check on something. La la la. Yes, we do have audio. That's good. So the other direction of things, he does a kind of sneaky argument here. Which I'll let you guys look at. I think I'm going to go on here if that's all right. But all right, so next up we have invertible, normal, isometric, and unitary operators. So theorem. Well, I guess I should do definition, right? Definition. If you have A, an operator defined in a vector subspace of E, what's E? Sorry, it's like, wait a minute, what's E?
is E just a normal vector space?
Is E his usual notation for a normed linear space? So he's like A from E to E, and then you have B from the range of A back to Well, it's not from E either. It's from, he calls it the domain of A to E, and this is back to the domain of A again. All right, anyway, what he's trying to say is limit the scope of the operator such that you're looking at just the range of the operator, and then the inverse will map just back to the domain of the operator. And of course, if they're actually inverses, what's that mean? A, B of x equals to x, and B, A of x, rather, let's say y, equals to y. I usually put y here, my bad. I mean, it doesn't matter. But this is for all y in the range. And this is for all x in the domain. So in short, I'm sorry that I wrote this down. All I'm saying is it's inverse of an operator. It's the same stupid definition as inverse of a function, all right? He's just fussing about the domain. Because he does, you know, there is some stuff in this book which is geared for, this book has envisions some subset of its students being interested engineers in graduate school. Like that is a subtext of some of the comments in this book. But anyway, so the theorem that he has, theorem 4.52, it says the inverse of a linear operator is, linear operator. So inverse of linear operator is linear operator. And an operator is invertible. A inverse exists if and only if AX equals to 0 only for x equals to 0. So in other words, the homogeneous equation has a unique solution. And it's invertible. A inverse exists if and only if x1, x2, xn linearly independent implies ax1, ax2, axn linearly independent. So it maps linearly independent sets to linearly independent sets, all right? And then finally, last is that if you have two invertible operators, if A inverse and B inverse both exist, then AB inverse exists and it's equal to B inverse A inverse. I refer to this as the Sock-Shoes formula, right? Of course, you've seen all of these in the finite dimensional context in your linear algebra course. And he says, it follows from part C here, which I have not labeled C, A, B, C, D, there we go. It follows from part C that if E is finite dimensional vector space and A is a linear invertible operator in A, then the range of A must be E. But that doesn't have to happen in infinite dimensions, all right?
We don't always have on.
Yeah, there's not exactly. So, vector spaces are infinite dimensional. Excuse me. Vector spaces over a field of characteristic 0, right? Reals or complexes or rationals. The cardinality of a vector space is infinity. But, and for functions, if you have a function on a finite set, right? A function from a finite set to a finite set, if that function's one-to-one, it's automatically onto. The function's onto, it's automatically one-to-one. So this is not generally true for functions on infinite spaces. Yet, for a vector space of finite dimension, if you have a linear transformation, which is onto, it's automatically one-to-one. Now we're talking about the context of a linear transformation on a vector space, which means its domain and its range are both in the vector space. So that dimension gives you a sort of finiteness That's why you still get that set theoretic result. This is some of that used car salesman stuff I told you about my brother sells. This is his idea, but this is not mine. That's not how I think. Okay, so example, what am I on? 4, 5, I don't know. 4. See, it feels like example 4. So here it is. You just do the shift operator. If you do x1, x2, dot, 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 all right? That's equal to 0, x1, x2, dot, 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 dot. So this is injective, but not surjective. On E equal to L2. So the range here is a proper subset of L2. But this is invertible. I mean, it's definitely an invertible map, right? If you look at the range, right? So, yeah. Yeah. It is not an invertible map on L2. You know, like, that's why this definition at the start's a little bit fussy. It's to deal with this issue of the domain and the range of the map having to be taken account for. But, well, anyway. Okay, so and then he's got an example. His next example, he gives you an example of an operator which is a bounded operator, all right? And it's invertible, but its inverse is not bounded. So a bounded invertible operator need not have a bounded inverse. So the formula is just this. AX1, X2, dot, 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 equal to X1, X2 over 2, X3 over 3, and A inverse. What's the formula for A inverse? X1, yeah, 2x2, 3x3. That's how to undo. That's how you undo what A did, you know? Easy enough to see that. And you can check that the norm, as is calculated over L2, is not, well, it's, okay, so for, notice L2 is, what does it do? It's square summable sequences, right? So in that particular example, what happens to you there is that you end up with a p equals 2 series when you calculate the norm of A, I think. Yes. So that's why it converges. The necessary series converges. But when you look at the other one, it's like the sum of n squared when you go to calculate the norm of the operator. And so, yeah, the inverse is not bounded. So then we have theorem 4.5.5. And here we have a bounded operator on a Hilbert space H. So A bounded on H. And we also want the range of A to be H itself. So it's a bounded surjective map. Then if A has bounded inverse, as we've seen, that doesn't have to be the case. If it has a bounded inverse, then the adjoint of A is invertible.